Yesterday, we introduced the divergence theorem, and we introduced divergence as some kind of a derivative. Today, we want to look at what binds all these things together as a derivative, and it is the del operator. The del operator we represent with an upside down triangle, like an upside down delta. It has a name that I don't remember. I just call it del. So just draw an upside down triangle. So the del operator is a vector operator. It's not just a vector sitting in space, it's a vector operator. It tells you to do a thing. It tells you to do this thing in particular. Partial with respect to x in the I direction, the partial with respect to y in the j direction, and the partial with respect to z in the k direction. So the del operator looks like a vector, but instead of having some kind of function, we have these operations, or these partial derivative operations. It's not quite a normal vector because it's not just a vector, it's an operation. It needs to be applied to something. Writing del just by itself is not really saying anything. It's saying to do something. It's like writing sine or cosine. We can't just leave like cosine hanging and have it mean something. It has to operate on something else. So the del operator is a vector. We have applied this. We can apply it to a scalar function, and we can multiply it by a vector field in two different ways. So we can apply it to a scalar function. When we apply the del operator to a scalar function, we produce a vector that we know as the gradient. So del f is the part, we're taking this vector and just applying it to the function f. We're applying this to the function f. We're not multiplying it by f. Well, our multiplication is apply the operation. That's weird to think about it that way. But do partial with respect to x in the I direction of the function. So the partial of f with respect to x, I. In the j direction, we take the partial of f with respect to y. And in the k direction, we take the partial of f with respect to z. This is the gradient of f that we are familiar with. In this context, the gradient tells us the direction of maximum increase. That's how we interpret the del applied to a scalar function. So del has smaller versions. There's an R2 version, partial with respect to xi plus partial with respect to yj. That's just the R2 version of the del operator, and it is the same gradient. Del has an R1 version, which is just our regular derivative. So instead of I, j, and k, we just have one direction, the x direction, not like the band. If we have just one direction, instead of partial with respect to x, we just say derivative with respect to x. If the function is just a function of one variable, mapping a real number to another real number, then the del operator is just giving us the regular derivative. Derivative with respect to x rather than partial. So you've been applying the del operator all along. A nice Palmolive reveal. We can apply the del operator. Now the del acts like a vector, and so we could use it in multiplication in two ways if we have a vector field. We can apply the del operator to a vector field in two ways, because there are two ways that we can multiply vectors. Specifically, we're going to do our three vectors. That way we get the two ways. That way we get the cross product if we want. We get the dot product and we get the cross product. The dot product del dot f is going to be the divergence of the vector field. The cross product del cross f is going to be the curl of the vector field, which we haven't really talked about. We talked about the scalar curl. This is the three-dimensional version of that. The curl of a vector field is a measure of how swirly the vector field is. That's a super technical term. That's why I say swirly, because I don't want us to think about it too much. It's telling us how much the vector field will cause rotation. How much is the vector field causing rotation? If we think about water draining down a drain, when we're far from the drain, we're not getting a lot of, well, let's go on the other side. We're not getting a lot of curl. But when we're closer to the drain, the water is swirling faster, we're getting a lot more curl. Divergence is how much the vector field is acting as a source. Curl is how much the vector field is curling. These are all extensions of the idea of the derivative, and they keep meaning different things. On the plus side, we get some stuff to calculate. On the minus side, we get some stuff to calculate. And that's sad because one of them is the cross product. We're like, cross product is messy. Dot product is pretty simple. You've got to remember that when we're multiplying, we're not multiplying partial with respect to x. We're performing the operation partial with respect to x. But so if we have a vector field that has these three components, f1 in the I, F2 in the J direction, and F3 in the K direction. Notice that F1, F2, and F3 are all scalar functions. They are the components of the vector field F. F1, F2, and F3 are all functions of X, Y, and Z, and they are the scalar components of the vector field F. This is how we build vector field. Scalar functions for each of our directions. If we take del dot F, we find the dot product. That's the partial with respect to X, partial with respect to Y, partial with respect to Z, dot F1, F2, F3. We know that this is going to be a scalar because the dot product is always going to be a scalar. And we can see what we need to do. Partial with respect to X of F1 plus partial of F2 with respect to Y plus partial of F3 with respect to Z. Partial F1 with respect to X is we can think of that as how the I component is changing in the X direction. Partial of F2 with respect to Y is how the Y component is changing in the J direction. Partial of F3 with respect to Z is how the Z component is changing in the Z direction. If we wave our hands at it enough, we can imagine that as being the source behavior of the vector field. Divergence. Here's the hand symbol for divergence. That's why when you're watching when you were watching mathematical competitions in vector calculus, they didn't have the referees were not equipped with like connections to the PA system, so that's why they had to have hand signals, right? That's why they still make the referees do the hand signals when they're out on the field, so they're like all divergence. This will just remind us of the cross product from way back in the day. We're taking this new del operator. This is our new derivative, more general derivative than the d over dx. And we're applying it to a vector field. We had two ways to apply it, because there are two kinds of multiplication, dot product and cross product. Here's the cross product. Now here we're going to take the partial of f with respect to x of f2. And here we're not multiplying those two things. We're applying this operator to the f2 function. So, that's a good question. Let's make this calculation and think about it. Actually, if we think about divergence, so del dot F equals 0. If we think about what the divergence is meant to represent, remember, divergence is how much a vector field is behaving like a source. So we get positive divergence if our vector field is behaving like a source, and we get negative divergence if it's behaving like a sink, going the other direction. If at a point there's a even amount of positive and negative, in our heat exchange example that we had yesterday, that would be like a constant temperature. Like stuff is moving around because there is temperature in the room, but the temperature is, if the temperature is constant, then at every point, the amount of movement out is the same as the amount of movement in. So it cancels out, and that's divergence of 0. If we think about it mechanically, the partial with respect to x of the I component is 0. Oh no, those might just cancel out. They're in different directions. I'd have to think about it mechanically. I'll have to think about it mechanically. But that means, so divergence 0, when del dot F is equal to 0, that means divergence is 0. And that means that we are not behaving like a source nor a sink. Everything is kind of balanced out. Let's see if I can think of a better example, a better description while we're doing cross product. So if we're going to calculate del cross F, if we're going to calculate del cross F, this is going to give us a vector because we're doing a vector product. The I component will be the partial of F3 with respect to Y minus the partial of F2 with respect to Z. If we grab the J component, take out this middle column. Take out the middle column. We'll have the partial of F3 with respect to X minus the partial of F1 with respect to Z. Then for the K component, still calculating our determinant, we'll have the partial of F2 with respect to X minus the partial of F1 with respect to Y. This is going to be a vector. This vector is describing how much the vector field is swirling around. It's not only telling you the direction of the swirl, but also how much there is, because it's a vector, it has magnitude and direction. So this is the curl of the vector field F. So we have a magnitude and a direction. This is going to be how swirly the vector field is. Yes. What's that? It is also going to be kind of normal to the overall spin of the vector field. So like if the vector field is spinning around on this table, if the vector field is spinning around, then the direction is going to be normal. So it's really telling us like the plane where the vector field is spinning. So as the air is spinning around here, if I grab the vector field and measure its right in this spot where my hand is, this is the swirl. Here's the direction of the curl of that vector field. And so here's like the plane of that the general swirliness of the vector field. This is also a test of whether or not you're willing to write the word swirliness into your notes. Because calculus is so serious that way. This is the one that we call curl of F, where we use the abbreviation curl of F for the curl of F. Even though in Green's theorem, we had the scalar curl. We had the scalar curl. And if we recall back to the scalar curl, that's the K component, because back in Green's theorem, we were working in the plane. And so instead of having an I and a J, we were just measuring the swirliness and everything was coming up out of the plane. So if we just grab this K component, this here is the scalar curl. Since we were back in R2, we didn't worry about the direction because it was everything normal to the curl was in the K direction. We couldn't really think of the scalar curl as a cross product because that was way back in R2, and we don't have a cross product in R2. But it is the minor of the K, the determinant, the cofactor of the K component. Any questions? How's everybody okay? Everybody looks super stoked. We're like putting all kinds of stuff together today. We've just taken the derivative and we're like generalized it to all kinds of different things. And even traced back to like our original d over dx, derivative with respect to f. Combine it with all the parts and stuff. And I still haven't thought about it with the divergence theorem. So we have all these different kinds of derivatives. We have all these different kinds of derivatives. We've got our original derivative, f prime of x. We've got our gradients of f. We've got the divergence of a vector field, and we've also got the curl of a vector field. They tell us different things. F prime of x gives us the slope of the line tangent to a curve at a given point. In that sense, it's the direction that the function is going. We've got the gradient. That's the direction of maximum increase of a scalar function. We've got the divergence, how much the vector field is behaving like a source. And then we've got the curl, which is how swirly the vector field is, and also what direction it is swirling. kind of your maximum swirliness. It's a vector, so it's going to be the maximum. So if there's a bunch of points that are swirling all around, they can be going in through three dimensions: left, right, up, down, front to back. The curl is going to tell us where the maximum is. And then if we're at a different direction, we just find the dot product like we always do. So I should say maximum. So we could actually figure out how swirly the vector field is in a particular direction with a dot product. Since scalar curl is a derivative, it is going to show up in a fundamental theorem of calculus. There is going to be a fundamental theorem of calculus for the curl. It's going to be a 3D version of Green's theorem. It's an R3 version of Green's theorem called Stokes' theorem. I don't know why these two have names and the other ones don't. Divergence theorem, I guess, is kind of Gauss, but that's tricky because like everything is Gauss. Every time he did something when Gauss was alive, like in the early 1800s, you write a letter, so, hey, Carl, I got this new math thing. Carl will be like, oh, it was Carl Friedrich Gauss, CF Gauss. Gauss be like, oh yeah, I did that. I didn't think it was that important. Like, oh man, I feel bad. I'm gonna publish it anyway. And then people will look at Gauss's old stuff. It's like, oh, look, Gauss did that. That's another Gauss's theorem. Meanwhile, you get to be forgotten. Any questions? Calculus really kind of opened up a door that was just like closed for a long time. So if you showed up like kind of like right after calculus, so like Cauchy, Euler, if you're wondering why Cauchy, Euler, and Gauss, like so much stuff is named like Cauchy and Euler, it's because they showed up like right after calculus. Because before it was like calculus, the calculus door was closed. And suddenly calculus door gets open. Newton and Leibniz is like, oh, hey, what's behind that door? And then they work on opening the door. It's like, we've opened the door. And then Cauchy and Euler just kind of like barge in. And it's like, oh, this is mine, 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 this is mine. This is mine. Leave some for the rest of us. And they're like, oh, no. All right. So tomorrow we'll talk about this 3D version of Green's theorem. Well, I wonder why these two have names and the other ones don't. All right, that's it for today. I will see you all on tomorrow, but have a good day and thanks for playing.